In this exercise, we are going to revisit um, the MNIST handwritten digit recognition problem that we solved using a very simple Gaussian model uh, uh, earlier in our semester. It's in that exercise that we have solved already. Um, the Gaussian model, the means and the standard deviations for each of the different categories were learned through the through a optimization process that's using all the training data. Once we have learned the means and the standard deviations for each of the different classes for any of the testing data that the training process haven't seen before, we can just compute its posterior probabilities by using our Gaussian model. So in that particular example, we achieved 89.9% of the accuracy, which is close to 90%, right? And it was a very simplistic model, and um, um, but here we have a more sophisticated tool, which is the neural networks, and let's try to actually solve the same problem uh, using a dense neural network and see how much better we can actually achieve, right? So, uh, so the model that we're going to try to construct is going to be a this kind of a multi-layer perceptron. It's a dense layer. Just it's composed of hidden dense layers, right? So it's going to be have more layers and have more neurons for each of the layer. But this diagram is just a kind of a simplistic view. Um, by dense, I mean that every neuron in the bottom is connected with every neuron uh, upper, right? So in the upper layer. So the arrows are going to be complete, right? So every arrow which is supposed to be there is going to be there. So um, and we're going to have like 3 hidden layers instead of just one jewel here, right? The structure is going to be more or less like the very simplistic example that we have looked at so far in our backpropagation studies, right? So um, except that the number of hidden layers is going to be 3, right? And then the number of neurons for each of the layer is going to be a lot more, right? Um, and then we are going to use a particular technique called dropout, right? The reason that we want to use this kind of dropout technique is because we want to prevent overfitting, right? So this kind of overfitting problem is going to occur once we have lots of degrees of freedom and our amount of training data is kind of limited. Um, and if this kind of things happen, which is indeed our case, the case in our example, we are going to have lots of weights, right? Because because neurons are going to be like a lot more, and then all the neurons are connected. We're going to have lots of weights. So the number of degrees of freedom is going to be like a very big number, right? And our training data is kind of limited. So how do we actually prevent overfitting, right? So we talked about overfitting uh, during our discussion about the regression problem. And in that study, we actually used two techniques to prevent overfitting. One is to limit the number of basis functions used for the fitting, right? The other one is by using a regularization technique that's called a reach regression, which limits the the size of the degrees of freedom, right? The coefficients of the basis functions. So for regression problems, you have that kind of a choice. And here we have a neural network. We have neural network. What's the kind of a common technique that's used for preventing this kind of overfitting problem, right? And it's called dropout. Dropout is you take out some of the neurons by random, right? And um, the basic idea is that if you actually remove some of the neurons, the number of connections are going to reduce, and then it's going to reduce the total number of degrees of freedom, right, for the system. It's going to reduce the number of unknowns. And why do you want to drop them randomly, right? So from iteration to iteration, or from batch to batch, if you drop those neurons by random, then the neural network is going to try to actually study or learn uh, the consistent pattern that's going to persist through different batches and through different iterations. right? Because the random noise is embedded inside of your training data, which is often the case. It's those random noises are not gonna be persistent, right? If you actually do this kind of dropout from batch to batch and from iteration to iteration, random noises tends to be random, right? It's not gonna be persist. Uh, but the signal that we are trying to learn is going to persist through batches and through iterations, right? So by choosing some neurons by random and then drop them, you are actually forcing the neural network to learn those consistent patterns or consistent signals that's persisting, right? And try to actually avoid fitting those kind of random noises. It's one of those commonly used techniques for regularization inside of a neural network, and we're going to use those dropout technique. My description is quite kind of complicated, but the implementation by using the Keras and TensorFlow, it's relatively straightforward. It's just a one line of code. You can actually add this kind of a dropout option to your neural network, right? So now let's look at the code, how we can actually implement the code, right? So before we do anything, let's try to import some libraries, right? We're going to use NumPy as MP and then import Keras. No, from Keras. From Keras, import backend. The name doesn't really actually, it's not really that important. So, and then from the MNIST dataset is actually embedded inside of the Keras. So once we have actually installed Keras and TensorFlow, we actually have installed the dataset, MNIST dataset, right? So from datasets, import MNIST, right? So we can just import the data without downloading anything because it's already comes with the package. It's still going to try to download something from the internet because but the code is going to take care of that automatically, right? So once we import it, we can load the data, right? And this MNIST sort of sub-library inside of these datasets is going to have an intrinsic function called MNIST.load data, right? And if we don't supply any kind of a existing path, then it's going to try to actually download it from the web. And then the output of this function is going to be like two tuples, right? And the first tuple is going to be the training data. And then the second tuple is going to be the test data, right? So that's going to be the process for loading and also separating the data into like the training set and the test set, right? And then X is going to be the features, which means it's all the kind of pixels or the grayscales of the different pixels of each of the image, right? And then the Y train is going to be the training label. It's a kind of a manual classification about what the image actually indicates, right? Is it a number 0 or is it number 7 or something like that, right? But once we finish loading the dataset, let's take a look at the number of unique training labels, right? So how do we actually do that? We just want to take a look at what's going to be some of the characteristics of the data, right? So let's print out some of the statistics, the data statistics, right? So what we are going to do is use the amp.unique function, right? And then look at Y train, right? And then return counts equals to true, right? And then that's going to be our unique counts, right? So and then how do we actually display that, right? How do we actually display that? So it's going to have two outputs, right? It's going to display the label itself and then the counts of that particular label, right? So all we have to do is to actually print, right? And then we can zip them together and then use a dict to hold them. So unique counts, right? And then let's just run the code and see what's going on, right? For now, we probably don't really need to import this thing, right? Maybe let's just leave it there. So, okay, so train labels 0, the number 0 is going to have like a 5,923, right? Number 1 is going to have like 6,700 something. And then goes from 0 to 9, right? That's exactly 10 digits. And then the number of training labels are going to vary, right? It's not exactly the same anymore. It's going to vary from label to label, right? So that's all the train labels. We can actually do the same kind of thing for the testing data. So how many training labels or unique training labels do we have for testing data, right? So, right. Test labels, right? So for test labels, 0 is going to have like 980, right? 1 is going to have like 1,135, this kind of thing. So testing data is a smaller data set. It's usually a smaller data set, right? So we're going to train our neural network using the training data and then apply our neural network, our trained neural network on the testing data set to see how well it actually works. So for testing data that's not used in the training, right? So the first thing we're going to do is we are going to have to actually convert those kind of training labels into the so-called one-hot encoding, right? We talked about one-hot encoding in a previous video, right? So if you don't exactly remember what one-hot encoding actually is, it's just so for now the labels are kind of digits, numbers, right? 0 to 9, right? But how do you actually convert it into so-called one-hot encoding, right? So how many labels do you have, right? You have 10 labels. So the number of labels is going to be what? Number of labels. Num labels is going to equal to, it's supposed to be 10, right? Right. So suppose if we run it, the number of labels is going to be 10, right? Yeah, it's a vector with a it's going to have like 10 labels, right? So what we're going to do is that we're going to create a vector with 10 elements in it, right? So if for a certain image, the label is 0, right? So it's an image of number 0, right? For example, right? That doesn't have to be 0. Could mean say number 8 or number 7 or something. It doesn't really matter. Internally, it could mean anything, right? But for example, 0 just means number 0, right? So if the image is the number 0, right? And then what you're going to do is that you're going to set that 10 element vector to all zeros except the first element, right? The first element in Python, it's actually the zeroth index, right? The zeroth index is going to have a value of 1. And then all the rest of the elements are going to have a value of 0, right? That's going to be the vector, right? But if it's an image of, say, number 7, right, then the entire vector is going to be all zeros except the, say, the sixth index, right? The sixth index is corresponding to, say, number 7, right? And then for that element, it's going to have a value of 1, and then all the rest of the elements are going to have a value of 0, right? So this is sort of the one-hot encoding. It tells you what? It tells you the probabilities for each of the image belonging to a certain class. So if it is an image of 0, then you are supposed to have the probability of 1 for the first element, right? And then probability of 0 for all the remaining elements, right? So this kind of one-hot encoding is a way for you to actually convert this kind of deterministic label into this kind of probabilistic interpretation, right? So if it's definitely an image of 0, then it's supposed to have the probability of 1 for the 0th element, right? So it's pretty much just that, right? One-hot encoding just means that. So how do we actually convert them into one-hot encoding, right? So there is a function called to categorical, and this function Where is it? It's probably in Keras utility, I think. From Keras utils import to categorical, right? So we import this to categorical function, and then we can actually do our conversion. Convert to one hot encoding, right? So y train is going to equal to 2 categorical y train, right? So so on the right hand side, we're actually taking y train as the input to categorical, and the output of the two categories, the one hot encoding vectors, are going to be assigned back to y train. So after this line, y train is going to have the label that's represented as one hot encoding vectors, right? So it's going to be a matrix, right? Because for each of the row, for each of the image, it's going to be a vector as a label, right? And then y test is going to equal to 2 categorical y test, right? So so that's going to be train and test. Let's just run this code to make sure that we didn't make any mistakes. Yeah, so now the Y train is going to be like 60,000 images and then 60,000 rows, right? And then 10 columns, right? Each of the row is going to represent the label of one image, right? Because now it's not a single number anymore. The label is not a single number anymore. It's going to be like a vector because of the one hot encoding. Yeah, that's pretty much all the preparations that we need to do, right? So now let's do some preparation on the input image, right? So let's look at the image dimensions, right? So image size is going to equal to x trend shape 1, right? Let's just run it and see what's going to be the image size, right? The image size is going to be 28, right? So it's going to be a 28 by 28 image, right? So 28 by 28, that's 28 times 28. That's 784, right? So you have this many inputs for each of the image. So you have to actually make sure that the dimension of the model actually fits that, right? So so input size is going to be what? Input size. So it's going to equal to image size times image size, right? And then what we want to do is to actually, for now, what's going to be the the dimension of the x train, x text, right? It's going to be 28 by 28, right? So for each of the images, it's going to be a 28 by 28 matrix, right? That's going to store the grayscale values for all the different pixels, right? So x train and x test, 60,000 and 10,000, right? Let's try to flatten them, right? So later on, once we do our CNN example, the convolutional neural network, we don't want to actually flatten the two-dimensional image into like one-dimensional vectors, right? But for now, we're going to flatten them because our neural network is going to be, the input layer of the neural network is just going to be a one-dimensional thing. It's so every input neuron is going to be corresponding to one pixel, right? And we flatten it. We flatten the image, and then it's going to be matched up with exactly with the input layer. There are certainly disadvantages of doing this kind of flattening, right? By doing this kind of flattening, you are losing the kind of a neighborhood information, right? Some pixels is supposed to be the neighbor of some other pixel, right? But once you flatten them, you lose this kind of a neighboring information during this kind of flattening, right? But for now, let's just do this kind of flattening and see what's going to happen, right? X train is going to equal to np.reshape x train minus 1 input size, right? And then x train is going to equal to x train dot as type float 32 divided by 255, right? So this way it's not going to be just the grayscale values anymore, right? We have normalized them. It's going to be having a value from 0 to 1, right? So this is one of the standard operations when we actually train a neural network. It makes them into like a range of 0, 1 is 0 to 1 is actually better, right? It's the training is going to converge faster. So and then X test, we're going to do the same thing. -1 input size, right? -1 doesn't mean actually you have a row number that's -1. -1 means that you want the Python to actually automatically compute what's going to be the first dimension based upon what's actually the second dimension, right? So it's and then X test is going to equal to X test dot as type float 32 and then divided by 255, right? So that's sort of the reshaping and the normalization. Now the X test and X train is gonna like have a second dimension that's 784, right? So you have flattened all the input images, right? Resize and normalize, right? Okay, so now let's try to actually build our network, right? Our dense network. So some hyperparameters, right? So batch size. So we're gonna do this kind of mini batch optimization, right? So the entire training data set is like 60,000, right? But we are, for each of the iteration, we are not gonna actually use the entire data set. We're just gonna take like 128 images out of this kind of 60,000, and this kind of subset is gonna chosen by random, right? And this is a number that's kind of can be optimized or adjusted, right? So 128 is just like an example number. You can actually try to change them. And then hidden unit, right? Let's just give it 256, right? So you're gonna have like 256 neurons for each of the hidden layer, right? And then we talked about the dropouts, right? What's gonna be the ratio of the dropped out neurons compared with the entire layer, right? All the neurons in the entire layer. This is called dropout ratio. And then let's just call it dropout. We're gonna give it some random number, say 0.45, right? You can try different different values, right? See which one actually gives you a better effect. Those are like hyperparameters that you can adjust based upon the results, right? Now let's build the model. Right. In the past, when we don't have this kind of Keras interface or Keras API, when we try to actually build model, we do have to actually use TensorFlow to write the model in kind of a individual functions, right? So if you want a layer with like 256 hidden layers, you have to write another function that's kind of build those layers neuron by neuron, right? But here we have TensorFlow. Here we have Keras, which is actually a high-level API that allows us to actually avoid building those kind of neural networks manually by using TensorFlow. So suppose I want this kind of model that's kind of layer by layer, right? And this kind of layer by layer model is called a sequential model, right? It's called a sequential model. So how do we actually use this kind of sequential models? The first thing we have to do is to actually import it. So Keras models import sequential, right? So once we have imported the sequential model, then we can use it. So model equals to sequential, right, as a function call. So this is gonna actually build a model. It's build a sequential or some kind of holder or some kind of container for a sequential model that's gonna allow us to actually add those layers, right? So once we have this kind of model container, we can add layers to it. So how do we actually add those layers, right? We're gonna add those dense layers. Dense layers means all the weights are fully connected. So all the arrows are gonna connect to are gonna be there, right? So we're gonna sequential is one of the functions, and then dense is another no, it's not in the model from dot layer import dense, right? And then later on we are going to add dropout. Dropout is another function call, and then activation, right? It's going to this activation function is going to decide what's going to be the activation function. And today in the past we have looked at the sigmoid, right, in detail, right? So today we're going to use a different one. We're going to use ReLU, right? The reason is that we are using ReLU is because usually those kind of asymptotic activation functions like sigmoid can have problems with diminishing gradients with the number of layers. So if you want to sort of look into it, this kind of diminishing gradient problem is difficult because when you do the backpropagation, you propagate the gradients or the derivatives from the output layer back into the input layer. It's going backwards, right? And the gradient is gonna reduce as you go from the output layer to the input layer. So by the time you get to the input layer, if you have lots of layers, right, the gradients are gonna be really small. If the gradients are really small, which means your convergence is gonna be really slow, right? Because your training, your convergence speed depends upon the gradients, right? So if your gradients are really small, then for every iteration you are not really changing the weights by too much. So so we have to actually avoid that, right? So and ReLU, this kind of ReLU activation function gives you some kind of opportunity for sort of reducing that possibility. So ReLU is kind of more useful for if you try to avoid this kind of gradient diminishing problem. The ReLU function looks like what? The ReLU function actually looks like this kind of thing. It's called a rectified linear unit, right? So it's going to be flat, right, for certain input values, right? So if the input value is like below 0, then you're gonna get no output at all, right? But once the input value actually goes above 0, then it's going to increase linearly according to y equals to x. So the slope of this linear line is going to be like 45. So as long as the input is kind of a bigger than a certain threshold, which is 0 over here, right? So the output is going to be proportional to the input, right? So if you take a derivative of this particular function, then the gradient is going to be like a 1, right? It's going to be like a 1 over here, right? And then it's going to be like 0 over here, right? So you are always going to have some value of the gradient. It's not going to diminish with the layers. So we're going to use this ReLU function. We're going to use this ReLU function as our activation function. So once you have this sequential model as a container, then we can add layers to it. So how do we actually do that? It's actually quite easy. It's just a model dot add, right? And then if we want to add a dense layer, we just call dense, right? It's a nested function call. So the output of the dense is going to be an object that's called a layer, right? And then the model is going to add that layer into this sequential model. So how many neurons do we want for each of the dense hidden layer, right? We want hidden units, this many, right? 256, right? If you change 256, then the number of neurons in each of the hidden layer is going to change also, right? It's automatic. It's all automatic. And then input dim is going to equal to input size. So this neuron is going to have this dense layer is going to have this kind of input dimension. That's the input size. That's matching what? That's matching input size 784, right? So you're going to have this many inputs, right? The number of neurons are going to match to that, right? And then model.add, we're going to have activation, right? And then this function actually takes a string as input, right? So if we want the ReLU activation function, all we have to do is to call activation and then give it a string ReLU as input. Then it's going to do all the kind of nonlinear conversions from the logits to outputs for each of the neuron based upon this particular ReLU activation function, right? It's a nonlinear function, right? And then model.add, once we have added this kind of a activation function, the next thing that we want to do is to add the dropout. with this kind of ratio, right? So it's going to randomly choose some of the inputs, some of the neurons to drop out, right? So 256, and then 0.45, about half of them are going to be dropped out, right? So and the neurons that's going to be dropped out is going to vary randomly from iteration to iteration, from batch to batch, right? So that's going to be like the structure for like a one segment of our sequential model, right? And then we are going to duplicate this kind of thing uh, uh, one more time, right? We're going to copy and paste this layer, right? Dense hidden units, right? But without the input dim, we're going to, because it's sort of in the middle now, it's not in the input layer, right? But we are still going to have the relu as the activation function, and then we are still going to do a dropout, right? So yeah, that's it. And the last one is going to be model add. We're going to add the output layer. It's still going to be dense, but how many neurons do we want in the output layer, right? It's going to be the same as the number of labels that we're going to try to actually make predictions for. So how many labels do we have? We have 10 labels, right? Because we have computed number of labels before. It's num labels. It's going to be 10 labels. So the output layer is going to have num labels, this many neurons, right? So if we have like 10 labels, we're going to make a prediction of 10 probabilities, right? Each of the probability is going to be the probability of the input image belonging to that particular class, right? Class of image. And then model dot add. This time the activation function is not going to be relu, but it's going to be softmax, right? So softmax is going to make sure that the summation of the predicted predictions are going to be exactly 1, right? Okay, so that's pretty much the structure of our sequential model. So it's going to be like a 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 lines of code, right? So if we want to look at a summary of our model, we can actually print it out. So this summary function is gonna allow us to take a look at the model itself, right? So it's gonna give us some kind of indication or some kind of information about what our sequential model actually looks like. It's yeah, you have to pay attention to the number of parameters over here. That's the degrees of freedom. That's the weights, number of weights, right? So that's this many, right? This is for the so how is it organized? It's going from like 6, 7, and then 8, right? So 8 is like the output layer, and then you're gonna have this many weights that's going into those output layers. Activation is gonna be softmax. It's so that's the total number of parameters. That's like close to like 20, close to like 270,000, right? Trainable parameters, that's 270,000. 270,000, yeah. We only have like 60,000 training data, right? So the number of parameters is like much larger than the number of training data, right? 60,000. This is 270,000. So we do have to worry about overfitting. So yeah, that's why we added the dropout, right? Yeah, that's the model summary. So once we have completed constructing the model, right? Once we have to actually compile it. So the next step is called compile, right? And during this compile process, we have to actually specify several things. The first thing is going to be our loss, right? The loss is going to be the objective function. It's how do we actually define the objective function, right? It's going to be categorical cross entropy, right? And we have actually talked about this kind of cross entropy, how it is defined last time in the videos, right? In the last video. And then the second thing that we want to specify is something that's called the optimizer. And we're going to use something that's called atom, right? what exactly is the optimizer, right? We talked about steepest descent or gradient descent method, which is actually uh, one of those optimization algorithms or optimizers, right? So if you take this kind of object-oriented approach to coding, then those kind of codes can be wrapped around, wrapped inside of an object. That's called a gradient descent optimizer or something. So, but in practice, a gradient descent or steep descent is kind of slow, right? Um, it has a slow convergence. The reason is that sometimes you have objective functions that looks like a very narrow valley, right? Um, if you have this kind of a situation, then the gradient descent or steep descent is gonna do this kind of zigzag thing and try to get to the bottom very, very slowly because it's gonna take lots of extra steps instead of just to go from the starting point to the bottom directly, right? So in practice, we don't really use steepest descent very often. The one algorithm that's used very often is called Atom. Atom means what? Atom is we have to actually import it um, from the library. So from keras dot optimizer import Atom, right? So it's called adaptive moment estimation, right? It's a widely used optimizer because its performance tends to be pretty good for many different kinds of problems, right? So it's gonna be a optimizer that we're gonna use. If you want to know more about this kind of particular optimizer, how it actually does the optimization, it's first of all it's something that's kind of adapted. So the learning rate is gonna be adapted to each of the individual weights. So how do you actually do that, right? When we did the steepest descent, the learning rate was kind of fixed for different parameters, right? We fixed a constant learning rate for the two weights that we were trying to actually code up by using the steepest descent, right? Which is a constant. It doesn't actually change from weights to weights. But Atom is going to try to actually we have a adaptive weights that's changing from adaptive gradient that's gonna adaptive learning rate that's gonna change from weights to weights. So it's not gonna be a constant. So it's gonna be adaptive learning rate. And this kind of adaptive learning rate really actually speeds up the convergence quite a lot, right? And the second thing that Atom does is that it also combines the so-called moment based gradient descent, right? So it's going to account for not just the gradient of the current iteration, it's also going to account for momentum from previous iterations. So it's going to have some kind of a memory of what's actually the direction that was taken in previous iterations. And those kind of a momentum thing can also speed up the convergence rate of the optimization algorithm in general, right? So we're going to use this Atom optimizer, right? I would actually recommend interested students to actually look into those optimizers. They are actually quite sophisticated these days, with lots of math, with lots of kind of careful considerations. It's very interesting. It's very interesting. And then the last thing that we're gonna input is called the metric, right? Metrics we're gonna use accuracy, right? So it's kind of a comparable thing that we have used in our kind of very simplistic Gaussian-based classification model for our previous MNIST work, right? So that's everything that's we needed for compiling the model, right? And then once we have finished compiling the model, all we have to do is to call the fit function. So this is gonna do the training. So we are gonna supply the training data and the label. And then how many epochs we are gonna use, right? We're gonna do like 20 epochs. And then batch size is gonna equal to batch size, right? So the batch size is gonna be what? It's gonna be like a 128. So every batch is gonna have like 128 images inside of it. So this, don't get confused about this particular line of code, right? On the left-hand side, this batch size is actually the internal parameter name for this particular fit function, right? It's an internal of fit. It's an internal variable name, and this batch size on the right hand side is actually the hyperparameter that we specified over here. So we are basically assigning 128 to this batch size variable inside of the fit function, right? So once we have finished calling fit, that's going to do all the training, right? And then all we have to do is to actually evaluate the model. So how do we actually evaluate the model? Again, very simple. Evaluate x test and then y test, and then again batch size is going to equal to batch size, right? And then the output of it is going to have a loss and then ACC accuracy, right? So by this time, all we have to do is to print test accuracy, right? And then it's going to be like a 100 times ACC, right? We want the percentage sign, right? That's the percentage sign. Yeah, that's all the code. That's all the code. 68 lines of code. That's enough for us to complete this exercise, right? And all we have to do is to run this code. Fit got an unexpected argument epoch equals to 20 epochs, not epoch 2 epochs, right? So okay, now let's run it. And then it's gonna do each of the epoch. We are gonna do like 20 epochs, right? And I'm gonna pause the video. We are gonna come back to look at the performance of the model after the training finishes. So now the calculation has completed, right? So the training accuracy was like a 98.18% right? So that's for the training. And then for testing, it's not too different. It's 98.2%, right? If the discrepancy between the accuracy for training and for testing are not so big, it means that the model is not overfit. Sorry, right? But suppose you have a training accuracy that's like 98%, but your test accuracy is only like 78%, right? That means the model is probably being overfit. So in that case, you have to think about it. Do you want to do more dropout or that kind of thing, right? Increase the try out different values, right? So, and then the test accuracy 98.2% compared with our very simplistic Gaussian classifier that we did in a previous study, which is about 89.9%, which is about 90%, right? So we have an increase of accuracy of about 8.2 or 8.3%, right? It looks like not much, but in practice, this kind of improvement is actually critical because people can actually use this kind of code to automatically classify the, for example, postal codes on envelopes, right? And a difference by 8% could mean like millions and millions of envelopes misclassified or avoiding getting misclassified when you apply this kind of algorithm to like lots of envelopes, right? So about 8 to 9% of improvement is quite significant in our case in this particular kind of example. And when we talked about the dense neural network, right, we did the kind of flattening thing, right? What I was saying is that this kind of flattening is going to give you some kind of loss of neighborhood or proximity information, right? So, and in practice, you do want to actually take advantage of that. And next time, we're going to try to actually use something that's called a CNN or convolutional neural network, which is going to take into account this kind of proximity information inside of the inputs and also the internal layers or hidden layers. So and this kind of CNN is going to improve our accuracy by small but still quite significant amount, right? Because the test accuracy is already like 98%. So how much can you actually improve, right? But for applications like automatic classification of envelopes based upon handwritten postal codes, those kind of applications, every 1% is going to matter dramatically in practice, right? So we want to actually improve this accuracy to as high as possible, right? So in the next video, we're going to talk about how to actually build a CNN and then use it to classify MNIST datasets.